Okay, hello, welcome back. My name is Athelham, and we're going to pick off on to linear circuits, which I forgot about last week. Or, well, I didn't forget about it. I didn't have enough time for it. So, we are doing 6 lectures worth of content today. And this is going to be covering over weeks 2, 3, and 4. So, let's get started. Alright, so last time, I can actually pull it out. Last time, we were talking about... We left off on independent we left off... Did we go over dependent circuits? Voltage sources? No, we did not. Okay, so... Last time we talked about ideal circuits, we talked about ideal elements and sources and independent sources, short circuit, open circuit. So this is where a lot of that stuff is going to come back to haunt us. So first, let's talk about dependent sources. So we've only talked about independent sources, and we've used that to kind of model things like batteries and current sources and stuff like that, but we haven't talked about dependent sources. Now, dependent sources are usually used to model transistors, mostly, because transistors are basically kind of a big part of amplifiers. Now you might be wondering, from digital circuits, transistors are only as things you use in digital circuits, not really for analog circuits. Well, wrong. Transistors are basically the whole basis behind amplifiers. So we use dependent sources to model these into linear circuits. For now, and I believe to ECU 240, or this course maybe even, go into more about transistors as well. So there are 4 types of dependent sources. So first type is voltage-dependent current sources. And everything here is a diamond shape, yeah, okay. So voltage-dependent current sources, so voltage... I'm going to only write this first one out, and then I will abbreviate everything else for now. So this one is VDCS. So voltage dependent current source. And this basically says, okay, let's say I have some other voltage in the source. The current of this one, actually, sorry, I should have this as VC, V control. If you have this elsewhere in the circuit, so this is it's called a control element because it controls. It's self-explanatory. But you have this current being some constant, so some coefficient multiplied by our voltage, and this constant has units amps over voltage, or inverse ohm, or Siemens if you are so inclined. Alright. And yeah, VC is a control voltage. And we'll go over some more other sources. So that's basically it for that one. There's also current. I'm going to call it current depend current source. So again, it's another current source. So this arrow tells you the direction the current is flowing, and it's going to be equal to, again, some coefficient of not voltage, but instead it's going to be a current. So now you have a control current instead. It doesn't have this. This one over here has no unit, so it is unitless because it's not converting any unit. So it's just going to be unitless. It's just going to be, I don't know, like 5 or 10 or 1.3. Next one is voltage depend current source. Sorry. No. Voltage depend voltage source. And so that will look like you have positive, you have negative, and you have VD is equal to, again, some coefficient times IC. And this bad boy over here, voltage dependent current source. So this this bad boy here has units V over A, or ohms, voltage over amperes or ohms, and it just basically blatantly uses Ohm's law. Again, you have a I messed it up. We'll fix it, okay? We'll put a C here. There, and everything's better. It's a current dependent voltage source. So, current, and it's this is control current, and then this source voltage, or this dependent voltage, will be some resistance times current. The last type is going to be is what I wrote down initially. Voltage depend voltage source. So this guy is, again, unitless, and you have voltage control voltage somewhere in the circuit that this source is depend on. So I will give a kind of a quick note before we go into our node and network laws. So I'm just going to element and network laws. Sorry. Ooh. I'm already skipping ahead to week 3. Element and network laws. Okay. So element laws are things that only relate to one element. So this is things like Ohm's law. I don't think I need to double check. Did we actually go over Ohm's law? Oh, we did not. Ooh. It's it's been a long while since I recorded the video. I don't remember what we covered and what we did not. But one example of an element law is Ohm's law, which we will cover. And where I talked about this. So it's really simple though. But if you want to, you can go back to the to where I introduced these and see how Ohm's law was introduced there. And network laws, it's things like Kirchhoff's voltage law and Kirchhoff's current law. So element law, network laws are mostly considered for, let's say you have elements in parallel or in series, and they start to make a network of let's say like voltages and currents. And for a series circuit, KVL and KCL, for like simple circuits, KVL and KCL will do you just fine. But as we get to more complex ones, you'll see that they are kind of lacking, and they get actually very computationally expensive. So we do some shortcuts and some I'd say we just abuse the hell out of some of the laws just to make finding equations and solving equations easier. So right, let's talk about resistors. So I think I mentioned last week that you can imagine electricity having being close to water, so where current is equal to speed and voltage is equal to a pressure differential. And I think I was mentioning that if you had, let's say, a clog, or let's say you had some residue building up on the sides of a pipe, that you'd have you'd have higher pressure here, right, and then lower pressure as it goes out of this constriction. And this constriction here, that's actually more technically conductance, but this constriction here is something known as resistance. I'll go ahead and say that this smaller area here, the actual the place where our water can go through, is something that we can call a conductance. And I will just say conductance. But I will touch upon conductance in a little bit, but not right now. I want to more introduce the idea of resistance. So, whenever we have a resistance, it induces a voltage drop to a specified current, and it gives a current drop for a specified voltage. It will make more sense once I go into Ohm's law, but resistors basically are think of a load of think of a light bulb, right? It consumes power. It does it. I think last week we talked about active elements and passive elements. Resistors are only passive elements. You cannot get energy from them. They will always consume power. I'm using power and energy kind of interchangeably here, but it doesn't matter because we're not concerned about time. I'm just more concerned that whenever you have a certain amount of charge going into a resistor, it will always consume that energy. It can release in light energy or heat energy or thermal energy if you're really that inclined. But suffice to say, it basically represents loads in our system. And results in voltage drop due to due to electrical energy, not engineering, being converted to thermal energy. That does bring up a very important law. Ohm's law. So Ohm's law says the voltage of a given element is equal to the current going through it and the resistance of that element. So if I had a current going through here, right, and I knew this bad boy's resistance, then I could figure out the voltage drop. Now, a little remark, before I get to remark, this resistance is measured in ohms. It uses the Greek symbol omega, which I'm struggling to draw. But it's given in this unit, and it's equal to volts over amperes. Or amps. It doesn't really matter. There is a remark to note about this. So, first note is that the voltage and current must comply with um, the passive sign convention. Comply with PSC, or passive sign convention. Whatever. Basically, it says what I wrote over here. I can't have what I can't have actually here. I'll just close this up because you don't need to see it. And that zooms me out. I love Excalibur, but sometimes has some drawbacks. But this is illegal. I can't have this. I can't have current going in the opposite direction to my voltage drop. Otherwise, that would mean that we are getting power from this resistor, which actually never, ever, 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 ever happens. In fact, resistors in real life are it doesn't matter of their orientation. So you'll always have a voltage drop no matter which direction you go with your current. You'll never have a voltage gain. Unless if you heat this resistor, I don't even know how you do this, but you could probably get some current out of it and it would be a voltage source, but again, that is not an intended functionality of the resistor. We are not mechanical engineers. We are electrical computer engineers, and gosh darn it, if we have to do mechanical engineering this, I don't know what I'll do with my life. But suffice to say, you'll have a voltage drop always in the direction of current. Yeah. Whenever we have there are two cases for resistance. Another note, it's the two cases of resistance. If, let's say, we have a resistance going to 0, then what that would mean is that, well, this V over A is going to 0, and A can't, either our amps get bigger or voltage gets smaller. We'll go with voltage instead, and we'll just say that voltage drop goes to 0, and that leads us to a short circuit. Because current is usually in circuits, current is something determined by the resistance and not the other way around. So once you have like a smaller resistance, you have a short circuit, and your current goes to infinity, basically. It goes straight through. It will allow the maximum current. In this case, if you had a physical wire, you'd have the current shooting up in that wire, melting it, and bad stuff happening. Second case is when our resistance goes to infinity. So this instead, well, this is this is where this goes, where your voltage over your current goes to infinity. You could make a case by saying that the voltage drop is going to infinity, although it's kind of counterintuitive. It's kind of difficult to think about when you're modeling a circuit. What we usually say though is that our current is going down to 0. So it gets really small, kind of, if you remember your rational graph, or people have reciprocal graph, people have different names, right? You would have this voltage going, kind of going closer to infinity here, as our current goes close to so our voltage going closer to infinity as our current goes closer to 0. And this would be here. This would mean an open circuit. I wanted to define it these ways because we already defined what a short circuit is and what an open circuit is. It's kind of hard to think about it as current goes to infinity, or as voltage goes to infinity. It's kind of easier to wrap it around your head when you have it going to 0. Now, because as I mentioned before, our passive sign convention only matters with like a passive sign convention is always complied with with resistors, which means you always have a voltage drop. You can actually kind of show what the power is for a given current and resistance, kind of using a shortcut. So if you substitute this V for IR, then that will give you I squared R. So the power of a resistor is the current squared times the resistor. If you instead did the other substitution and did I is equal to V over R, then you'd get V squared R. Sorry, I'm going to kind of rewrite it here. V squared R is equal to I squared R, like that. So if you have the voltage for a resistor, or you have the if you have the current for a resistor, you can determine the power consumed by the resistor just by knowing the resistance of the resistor itself. Man, I'm saying resistor so many times. So you can also, another thing to note is that you can see that V squared and I squared are always going to be positive. And no, we are not going to we're not going to go into complex numbers. I would assume complex numbers could actually do some supply power. Maybe not. I will get to that later when we cover in class, because I suspect it could happen if you have a complex number for your voltage or your current. But for the sake of argument, we're just going to say that voltage and current are always in the real numbers, so we're going to say that they're always positive for V squared and I squared. So that always means that we consume power, or we absorb power, right? Because this is saying absorbed power here. When I'm writing P here, I'm meaning P absorbed, right? In the real world, for power, you have, for a resistor, you have usually power rating. For the small resistors that you can usually find for cheap online, like they have this like a few bands and whatnot, these are usually about a quarter of a watt, or they can even be in half a watt. But these power ratings are something that, these are like basically maximum power ratings. If you were to exceed these, then your resistor becomes a light bulb. That's not something you want, not in any circuit, unless if you want to do that. But and suffice to say, you want to usually not exceed these values. I did mention about conductance, and I would think I was going to say about something about voltage as well. So get those two things out of the way. First thing is a remark that I want to kind of say. If you are analyzing a circuit, let's say you are analyzing the voltage values of a circuit, never ever think about current directions. What do I mean by that? Let's say you have a circuit in parallel, and you want to find the voltage consumed by, consider like a series parallel circuit, right? You have a battery, you have a resistor, right? The voltage, let's say you want to find out the voltage, you could say, okay, using, I think we went over it last time, that the voltage between two nodes, right? If you have two elements in parallel, the voltage between that node will always be the same between these. So this V source and VR, they're equal. You might be tempted to think, okay, but let's say we have a current, right? And this current goes around here, and you say, okay, well, why don't we use passive sign convention? except that you don't want to do that if you're strictly concerned about the voltage. So keep in mind that it's something very important. If you want to determine voltages of, let's say, something, if you want to say, like, talk about voltages without any relation to power or resistance, don't ever think about current. If you need to, then sure, that's fine, but if you're strictly talking about voltage, never, 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 ever, ever, ever talk about that. Otherwise, it's going to confuse you, and then you'd have this situation happening where it's negative, because which would not work at all, ever. So just keep that in mind. Second thing is conductance. Now, I talked about conductance just a bit, and conductance is denoted with the letter G. Alright, it's equal to 1 over R. So the reciprocal of resistance, and it has units inverse ohm or Siemens. Sorry, equals S. So you use S for Siemens, but you can also use inverse ohm. Up to you, really. And it just basically measures how good current can flow through a conductor. It's the opposite of resistance. What more is there to say? That brings me back to kind of what happens when you have, like, what I talked about is, like, you have two elements in parallel, two elements in series. What happens to their voltages and what happens to the currents? I didn't talk about, like, I didn't really go too much in depth of that, but we will go into more detail about that. So now I will introduce to you some network laws. Right, but first, we have to do a definition. So a node, okay, is a point in the circuit where the voltage is equal, or two or more elements are connected. So let's say we have a circuit, we have a resistor, we will make a voltage source over here, and you have a resistor, and here, resistor again. So this point, let's call this point here, actually I'm going to name them everything, A, B, C, D, E. Okay, so let's consider these as nodes. So, point, I'm just going to write it out. Point where more than two elements are connected. Okay, there we go. So, let's take a look. Okay, so A here is a node because it connects this power source with the voltage source with the resistor. B here is a node because it connects three resistors together. C and D actually here are the same node. So, no matter along this line, it's the same node. Although I give it a point, keep in mind that we could just as easily write this part of the circuit as like this. And I haven't changed anything about the circuit. You might be wondering, oh, but wires and the wires, we consider that these wires are magic wires, right? No resistance. No resistance, no capacitance, no inductance, no funny nonsense. We consider that these are like the bee's knees of conductors that like they have. Basically, think superconductor, but like perfect superconductor. It's magic. But so in that case, no point along this line here will actually be at a different voltage or current than from each other. E and F are also a duplicate, so I'm going to get rid of F here. because F here is separated from E with a short circuit, right? So our only real nodes that we consider is A, B, C, and E. Now, now there is, so that's everything about it for nodes, and there is one more thing I want to talk about. Well, actually, two things I want to talk about. So a loop is basically a closed path in a circuit that kind of loops around. They kind of go around in. You could do it clockwise or do it counterclockwise, but it's just saying like a kind of a closed path around a circuit. So you can't have an open circuit and that's considered a loop. That it's not a loop. It needs to be closed, right? Like closed circuit television, CCTV, and we can actually make some loops over here. So we have one loop, right? So we call this L1. We have another loop, and we'll call this one L2. And then we have another loop around the outside that we'll call L3. Okay, so this is a loop. It looks like a loop. There is a special subset of loops that I want to kind of touch on, and that's something called a mesh. A mesh is a loop that does not enclose another loop. A loop, right? So in this circuit here, we have 3 loops, and that's L1, L2, and L3, right? But we only have 2 meshes, and that is L1 and L2. L3 is not a mesh because it encloses L1 and encloses L2. Also, something significant to note is that for a loop, you only have one element considered. So I don't consider this battery twice as I go around. I only consider it once, like I cross it off, then this resistor, and then I'm done. No more elements, unless you want to count short circuit being 0 volt and infinite current, and I'll move on. Okay, so those are the definitions out of the way. Let's talk about Kirchhoff's laws. So the first one we'll talk about is Kirchhoff's current law. So Kirchhoff's current law. And that's actually about the same. I thought he was Russian, but he's actually from Germany, or from Austria, or from Belgium, I think. He's he's from either Germany or Austria. I'm saying either one. But suffice to say, this is a new law. Okay, so what this basically says is that the algebraic sum of currents leading nodes. So what I mean by algebraic, I mean positive or negative. I'm saying positive or negative voltage current here. Algebraic sum of currents leaving a node. Leaving and entering a node is 0. So if you have, let's say you have a node, right? You have node A. You have current 1, you have current 2, you have current 3, and you have current 4. So currents entering a node are taken to be positive, and the current leaving the node is taken to be negative. So here we have I1 plus I2, sorry, no, plus I3 plus I4 minus I2 is equal to 0. This is true for any node, and that's all for Kirchhoff's current law. It just says this, that all the nodes entering or leaving is equal to 0. And move on to the next law, which is Kirchhoff's voltage law. And I scrolled too far. And basically this is saying, okay, if you go in a loop, right, if you go in a loop, or yeah, in a loop, so it's just saying that the algebraic sum, so again, we take voltages to be positive or negative, sorry, of the elements in a loop, all elements in a loop, sorry, I should say, is voltage of all elements in the loop is 0. So if you have, let's say, a voltage drop here, a voltage gain, and a voltage drop here, then you'd have negative V1 plus V2 minus V3 is equal to 0. That's all it says. And there are some more examples. Yeah, but something to note is you can try to use only meshes, because for the example circuit above here, right, if you were to take KVL around, I'm going to start referring to Kirchhoff's current law and Kirchhoff's voltage law as KCL and KVL. If you take KVL around a loop here, and you take a KVL around a mesh and KVL around another mesh, and then you take KVL around this loop, you'll find that these elements here are repeated in the outer loop. So for KVL, you only need to do meshes. You don't need to do the bigger loops. You don't even need to consider them, because they are they're not going to be independent. You can always just find everything that you know about the outer loop from these meshes. It is still an option if you can't do KVL on a mesh, but generally you should be able, you should usually be able to do that. Because if you do this, then the number of equations you have is equal to the number of meshes, and if you have less equations, the better, right? You don't want to add more equations and add more work, so you want to do as least possible amount of work. Something to note though is that for parallel elements, the voltage will be the same. So if you were to take L1 over here and you take L2 over here, it's already you would see that this voltage here and this voltage here, well, these two voltages over here, this the resistance to voltage drop would be the same, kind of, because it would look like this, sorry. Right, and there's the rest of the circuit, and these two are in parallel to each other. So if you were to count, if you were to go along with L2, you could see, okay, well, this is between two nodes, so, and you take it opposite direction here, so this one would be, let's say, In this direction it'll be negative, in this direction it'll be positive, right? This negative must balance these positive numbers out, or else it will violate KVL, because they need it all to be 0. So you don't actually need to do KVL for elements in parallel, but they are really helpful for elements in series. Now we cover equivalent elements. So let's say you have 3 resistors. I'm going to actually label these. I haven't labeled any of them previously. You should label your resistors like I have here, but oh my god, that's a bad resistor. Sorry, that. So let's say we have 3 resistors in a row. We can actually simplify this to our resistor on the right here. It's actually not too hard. Reason why we want to do this is to, again, simplify our equations, because once you get all the KVL and KCL stuff, it'll become a system of equations and go from there. But this is actually pretty easy. If you could do the, I'm not really going to go for the derivation of it. If you're really interested, you can. But if you have 3 resistors in here, the equivalent series resistance, or ESR for short, is going to be equal to R1, 1 over R1 plus R2 plus R3. You could actually generalize this to be R equivalent is equal to 1 over the sum. Sorry. Oh no, that is bad. That is bad. Oops. No, it's not 1 over. I misread. Ignore. It's going to be right. If this is going to be the sum of all the resistances, it kind of makes sense if you have a given. I forgot to talk about it. I forgot to talk about it. If you have a given current, right, the voltage drop in these will always, the current is going to be the same throughout, so the voltage drop will be the same regardless of the current, so you always have the same voltage drop. I neglected to mention this, but if you have, let's say, a fixed current going through, so you have, like, let's say you have a resistance, right, and you were varying the current here, the voltage drop over the resistor would also change linearly with the current changing. And if you had, let's say, you were changing the voltage here, that also means you're changing the current linearly. Works both ways. That's something that I wanted to mention. So that's everything for equivalent series resistors. Now, you can also do the same thing for equivalent parallel resistors. So let's say you have some resistors, so R1, R2, and R3. You could actually convert this into an equivalent resistance as well. However, you get a little bit more. Derivation is again complicated, but so the 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now you could do Req is equal to 1 over, and then swap it out. But I think you can already see that this equation is already pretty messy. So you can actually change this to be in terms of conductance. So the equivalent parallel conductance is equal to the conductance of 1 plus the conductance of 2 plus the conductance of 3. All right, and remember, conductance is equal to 1 over R. Right? And you could actually generalize this again, that the conductance of parallel resistors is going to be the sum of all of the conductances. There is two special cases that I want to mention for parallel resistors. This is, I didn't even write it. Equivalent parallel. Sorry, it's gonna annoy me if I don't write this correctly. So hold. I will parallel resistors. Okay. There you go. Equivalent parallel resistors, and I will write it out here. It's already getting messy, but you know what? We'll work with it. We'll roll with it. But the two special cases I want to mention is two parallel resistors, and it's actually really nice. So if you have two parallel resistors, R1 and R2, then their equivalent parallel resistance is equal to their product divided by their sum. Okay. The second special case is parallel with a short circuit. Parallel with short circuit. And so if you ever have let's say resistance is equal to 0 here, then this top part will be 0 and you'll have to 0. So if you have, say, your circuit looks like this and you have a short circuit being parallel with it, then this resistor has 0 voltage drop, right? Because then these would have to be equivalent. Yeah, so so if you use this, just remember you're not use this as a resistor in parallel with a short circuit. Okay. And yeah, yep. Okay. So there is another thing with parallel and series resistors that we will talk over about, and that is let's see, we'll start off with the voltage division. So voltage division states that if you have, let's say, 3 resistors in parallel, so like what we have over here, right, then you can get the voltage over any one of them. Let's say V1, V2, V3. You can get the voltage of any one of them if you know the overall voltage drop by basically kind of stepping up your game with the equivalent series resistance. So V1 here will be equal to R1 over REQ, so the equivalent series resistance of the entire set of resistors times the voltage, the overall voltage, so that you could expand this to R1 is equal, so R1 over R1 plus R2 plus R3 times the voltage, and that will be your first one over here. You could then do the same thing for the other ones, and they're just gonna be the same thing. So you have R2 instead of R1 plus R2 plus R3 times the overall voltage, and then the same thing for here. So R3 over REQ, and that's going to be equal to, you guessed it, R1 plus R2 plus R3, and that's going to be multiplied by the voltage. That is voltage division for you. There's another thing, though, called current division. And this applies when you have resistors in parallel. So let's say you have this case. I made a mistake there, but it's fine. Here, it's going to be the same thing. It's going to be the same thing. So if you want to know the voltage 1, voltage 2, voltage 3, right, you have positive. Again, they all follow positive sign convention. And sorry, no, not voltage. Oops. Oh man, I am really losing it today, aren't I? So, and you have the overall current. Then you could basically do the same thing as you have over here. So current 1 is going to be equal to, it's going to be conductance over the overall sum of conductance. So equivalent G equivalent. So that'll be G1 over G1 plus G2 plus G3, and this is going to be times the current. And again, I will save you the headache of writing them all out. So the other three you could do Look how easy it is. I prefer this over paper notes. Even that there. Right. See? And there you'd have for current division. So if you ever have 3 resistors in parallel, you can use this to get your currents individually. And this is really helpful because you know the current will be the same through series, and your voltage will be the same through parallel, and this is really helpful for finding the other one. So voltage for the series stuff and current for parallel stuff, where KVL and KCL really shine. Man, this feels kind of. No, it's not really obvious. Sorry, I didn't even know it before I started. So basically, you can also kind of apply this to sources as well. So let's say you have voltage sources. So again, we're doing ideal sources here. We're not doing physical ones. And basically, let's say you have a source here. You have another source here. You can add these two up, and this will give you a new source. So V1, V2 is equal to V1 plus V2. I'm going to call it V total. And if you did, you could actually reverse one of these voltage sources. So let's say you had this one flipped, right, V2, and this one here, we can actually still represent this as V total is equal to V1 minus V2. Because this one's going in the opposite direction, it makes sense that it's subtracting from the voltage, right? If this one was, let's say, you have a given current, right? This one would be supplying power, this one would be absorbing power. It doesn't really make sense for the source to be absorbing power, but here we are, and you can have it. It just means that your equivalent voltage is going to be subtracted. You can also do the same thing with current sources. So something to note again is that if you have 2 ideal voltage sources in parallel, that won't work. And if you have 2 ideal current sources in series, that won't work either, but we will consider the other cases in which they are valid. So let's say you have 2 current sources, right? Right, and excuse the crappy drawing, but if you have I1 and I2, you could make this into equivalent current source, or I total is equal to I1 plus I2. Now you can do practically the same thing, except let's say you have a current source in one direction and the current source in the other direction. Right. Keep in mind this is where the arrows are going to do. Well, I mean the plus sign also mattered here. You could actually very easily, if you you could actually very easily go the other way and have v2 minus v1, but we're going to just consider one direction for now. Let's you have I2 and sorry, I1 and I2, then this would be an equivalent current source of I1 minus I2. Right. That actually wraps up everything for week 2 for now, I think. So we're going to go on to week 3. So we have talked about KVL and KCL, how they are used usually, but we want to kind of speed things up here, because KVL and KCL, if you were to do all the equations, they are very slow. Like when you get to bigger circuits, I mean, they are very slow, they're very tedious, and so you just don't want to do all of them. Right. So what we're going to do is something called node voltage analysis. Content still. Okay. So let's start off with some definitions. So, essential node is a node where you have that has greater than or equal greater than or equal to 3 elements connected to it. And why it's called essential will be, well, kind of make sense in a bit. Second kind of node is a reference. Second kind of thing is reference node. And this is where we assume that our base voltage is equal to 0 volt. It is chosen arbitrarily. You could choose anything to be a reference node, but usually, most of the time, you pick an essential node to be the reference node, because you want it. Because you kind of see in a bit why we want our reference nodes to be essential nodes. Otherwise, it's going to be very difficult. More difficult. Not very difficult, but more. Right, and it's actually what you refer to as ground. So when you're measuring voltage to anything, it is in reference to something else. Usually when you are testing voltage, you have to pick something compared against, and we usually use ground, right? Or the reference node in this scenario. We denote this reference node actually with one of 2 symbols. So either use this one or use this one over here. Alright, and these just both mean ground. We also have another definition, which is node voltage. And this is the voltage drop from a non-reference node to the reference node. So voltage drop from non-reference. So it would be kind of stupid to check the voltage from reference to reference, because it will be because it will always be 0, because it's short circuit. Okay, so a little bit of this node voltage analysis is basically KCL on steroids. So you remember how KCL we had currents leaving and entering a node, basically, instead of thinking in currents for that, think about using voltages instead. Because if you recall, well, if you recall, we can use Ohm's law to relate our current and our voltage. So if we know our resistances around a node, then we can actually go ahead and solve for voltages. You'll actually see this in a similar pattern to mesh analysis, which I will cover in just a bit. So let's say we have a circuit. Again, I'm just making whatever circuit here. And you could have a voltage source. And this one is going to be our reference node. So usually when we're picking our reference node, we use the node that has the most amount of connections. So here there are two good ideas for a reference node, and it'd be here or down here. So we're going to actually just give these nodes names. C and D. I'm just gonna draw another node because it kind of illustrates the point. No, that's here. I just want a slightly more complicated circuit. This one will be E. Sorry, that one. Well, that one will not be. That one will still be B. This one will be E, and this one will be F. Okay, so here A is non-essential because it connects between two elements. D is also non-essential. B here is essential because it connects between actually four nodes here. E is not essential, F is not essential, and C is essential, and it's the reference node. Anyways, you could either pick B and C here because they're good options, but let's say if I had, say that one's all just one line, okay. Let's say instead I had a resistor here, right, and another resistor here, then I'd have another node here called G. G wouldn't be as good of an option to use as a reference node as compared to either, well, in this case now C, because it has four connections. So you want to pick your reference node carefully, because then it drastically simplifies things. So I have a whole thing about a procedure for nodal analysis. So I will kind of say it. Actually, I can write it out here, because trust me, you do not want to see me like writing this with my hand. So there's a procedure for nodal analysis, and basically this procedure. Okay, so first you want to choose the reference node and label, I'm going to combine my one step, and label n minus 1. So n here is the number of nodes that you have. So number of I should have included this. For a circuit with n essential nodes. Because, spoiler alert, non-essential nodes don't care. Don't use them. You should never be needed to use a non-essential node. Anyways, enable n minus n nodes, or node voltages. So a node voltage, right? Example of this is, let's say I have a V1 over here, right? Or let's say V2 over here for G, right? V2 we can trace to the reference point through this resistor over here, right? And that's kind of the basis of node voltage analysis. Right, choose a reference node and label n-1 node voltages, so you have to label them. And assign currents to branches. Here's where you see that I should really use a typing class. This one is actually optional. It's not something you really need to do, because we it's kind of more like an intermediate step. Once you like get better at node voltages, like node voltages, then you don't really need to do this, but I will put it in for now. Our third thing is to apply KCL at each non-reference node. So don't ever apply KCL to your reference node because it's useless. Non-reference, again, essential node to get n-1 equations. So KCL for all these node voltages that you have here, these node voltages should be your essential nodes. You'll have n-1 equations. Don't be scared that you have multiple equations. I'm assuming that you know linear algebra and you know several different ways to do linear equations. You could use Cramer's rule. You could use Gaussian elimination. Gaussian Jordan elimination. You could also use substitution if you're a masochist. But you can use you can solve these equations however you'd like. So apply KCL to each to get n-1 equation. Use Ohm's law and KVL to express the currents in terms of the node voltages. So here this is where you use KCL, but you also use KVL as well in terms of node voltages, and then you basically solve the I can't type n-1 equations for the node voltages. For the unknown n-1. Right, because they're going to be unknown. So how would that look like? Let's take a look. I'm going to give like a kind of a brief overview. So you want to basically take a track of all your currents. There's 3 points rule. Sorry, well actually it's oh wait, no, 3 points rule is actually really simple. So 3 points rule. This is basically, let's say you have two node voltages, V1 and V2, and you have a resistance in between them. So you have resistor, the value R, you have V1 at this point here, and you have V2 at this point here. They're both node voltages. So let's say you have a current IX, you have current IY. Here I'm going to mention that these currents are going to be, could be either way. So you have voltage X, which represents the voltage drop caused by the resistor in accordance to your current. So you could say, okay, that let me just make sure that we have the right directions. Okay, so IX here will be equal to V1 minus V2 divided by the resistance of our resistor, or it's equal to Vx over R. here, Iy is equal to v2 minus v1, or is equal to negative vx. And again, everything is over r. Surprise, surprise. And you can actually show that this one is actually just equal to negative ix. So it's very similar to linear algebra, where let's say you have like a global reference point, like a zero vector, right? And you compare all other vectors to that zero vector. If you want to see the the difference between two vectors, you actually have to subtract them, and it will get you the vector between those two vectors, right? So you have origin, vector 1, origin, vector 2, and this one's going to be vector 1 minus vector 2. Alright. So, that is node voltage analysis, basically, in a nutshell. There is another thing, which I kind of hinted towards, which is called, I'm getting too ahead of myself. Hold on. So basically, let's say you have a voltage source over here. The problem with voltage sources is that they kind of mess up our they don't mess it up. They make things really complicated, because you want to, let's say this voltage here. You could have more equations for going around here and going around here, and this voltage source actually would be how to put it, it'll make everything a lot more complicated, and we want to eliminate that. Because remember here that we determined our currents here by knowing our node voltages and solving with resistors, right? So no, we don't know our node voltages, other way around. We know our currents here, and we know our resistances here, so we can find our voltages between 2 points. But the problem is, for an independent current source, for a voltage source, even a dependent source, I'm pretty sure too. Actually, no, you can use dependent sources as part of the equation, I think. Okay, never mind. I may have not have done too much practice on this, so forgive me. But if you have a voltage source over here, it'll mess up your current calculations, because how can you model the resistance going through here? So what we do is we use something called a supernode, right? Once everybody's super, nobody will be. So this is a supernode, and this is where you can kind of abuse the hell out of KCL again. And supernodes is basically just treat it as one big node and solve it like you would regularly. So instead now, because this one is around the reference node, this is also a reference node here, right? And you can solve for other node voltages here, which actually brings me to, I think A and D here are going to have a voltage of 0, because it's shorted with it. Or they might not be, but you can actually solve your equations first, and then you will put in your voltage sources after. Okay, that's okay. It was just it's just one summer mark I was taking a look at. Sorry. If you have a current source here, and then you have a resistor in series, this resistor has no effect on current. So you can actually ignore it, but kind of not, because it does have an effect on voltage and power. right? So if you ever have, and you can actually factor in your current sources as well into your equations, because you can just add the currents up. You don't actually have to use Ohm's law, which is great, but you could just include them in your calculations. Like an example of how this would look like. Let's say if I wanted to find the node voltage for, let's say G over here, right? G, I could put it to the reference node through R, right? And I'd kind of assume, okay, this current goes in that direction. So we'd have V1, V2, so our current going out of G, so is going to be negative I1 here, sorry, negative I1. I'll say this one is also going out, and this one's going in. You could, again, these can be arbitrary, and you can solve for your equations, because we don't really know, we can't really say, oh, this is the current definitively, so we use node voltage analysis to see if our assumptions are correct. I mean, you have I2, I3 here, so I2 here is leaving as well, but you have I3 going in is equal to 0, and then you could represent this as V2 minus 0 here, because we take our reference to be 0 over R, and then we have, let's say, R1, then we have R2 here, minus V2 minus 0, and R2, and then you could go around and figure out this as well. It'll be something with this with these equivalent resistors. You could eliminate them, and you could find the current going through them. So actually, it would actually be this current, because they are in series. So it would be plus ID is equal to 0. Solve for V2, and Bob's your uncle. You're all good to go. The next thing I want to talk about is something called mesh analysis. So it's very similar to node voltage analysis, except now you're doing meshes. So sorry, I'm just going to kind of yeah. So we start with a definition. Again, can't start a new concept without a new definition, can't you? So definition of a mesh current is imaginary. A current that flows around a mesh. Regardless of branch currents. So you might remember that what I mean by branch currents here is, let's say you have, let's say if current here you have I1, I2, I3 here would be a branch current, right? Or I2 here would be the branch current, but you would go around in a loop like here, and you kind of ignore I2 for now and just say, hey, I2, sorry, but you're not invited. So let's say we have a circuit, right? And here we use KVL instead of KCL. Sorry, mesh current and node voltage are so, how to put it, they feel kind of counterintuitive to me. They make sense, but they feel kind of weird even to me, even after I've kind of absorbed this information. Just knowing that voltage KVL is in terms of meshes and loops, and KCL is in terms of nodes and currents entering and leaving a node, but then mesh analysis and node voltage analysis kind of flip it on its head. So here, let's say you have a circuit, right? You have a circuit, and so you would travel around in a loop, or in a mesh. No, you don't do this loop. That's not what I wanted to do. And you go around and say, okay, kind of say current drop here, which is kind of strange, but you have, so you go around and you say, okay, does this voltage here comply with my loop over here? So here we always take resistors to be in the same direction as the loop, but but for this one we have our voltage sources in the other direction. So what we do is we say, okay, we kind of assign a current. So we have I2 and we have I3, right? So we have I1, which is going to be this one, and we have I2, it's going to be this one, is equal to, so this one goes in the direction, this one goes in the direction, and this one does not go in the direction, right? And we just say that it is equal to 0. We do the same thing here. So I2 is equal to, so I3 is now, sorry, I3 here is actually going to be in the positive direction. I don't know why I said it was in the negative direction, but it will be in the positive direction. And I2 here, I3 is actually going to be in the negative direction, and then we have I4, which is going to be in the positive direction, and we have I5 over here, which is going to be in the positive direction as well, and that is equal to 0. You could go ahead and this one will be the same thing as 3-point rule. So yeah. Yep. Okay. Again, similarly to node voltage, you can actually take super meshes whenever you have current sources to eliminate them and to make your life a lot easier. And here you would take the resistance times the voltage drop over these elements, and that will give you overall current going through your meshes, right? I'm going to write out I'm going to also type out the procedure again. Otherwise it's going to be kind of messy. However, I will make some remarks before I type it out. So in KVL, right, voltage drops. So voltage drop is taken to be negative, and voltage drop is taken to be positive, and voltage rise is taken to be negative. So I need to review something. I checked my something and I did it right. I'm good. Don't worry. I didn't lie. So yeah, voltage drop is taken to be positive, and voltage rise is taken to be negative here. So this voltage here is a rise, so it is actually taken as negative here. Again, another thing to consider is that in the direction of movement here, a resistor is always a voltage drop. Right? Again, passive sign convention. Our current resistor can accept current both ways, so we want it to be in the way that consumes the power, which makes the most sense to us. And branch current if the resistor will always be in the direction of voltage drop. or direction of movement that I've illustrated here. That's everything. There is the concept of super mesh as well. So if you could actually combine two meshes when you have, let's say, instead of a voltage source here, you have a current source. But that's but that again, same thing as having a super node. It eliminates complexity, and you can just use that to go around your circuit. Now I will actually just type out really quickly the procedure for mesh analysis. So procedure for mesh analysis. And you know what? My typing is going to be slow and inaccurate. You already know it. And this is for a circuit with n meshes. So you want to draw and label mesh currents. Second thing you want to do is you want to write KVL around each mesh. Right, so I didn't do I did do it here. That should be fine. For your voltage sources, actually, that's. Oh wait, no, sorry, it shouldn't be I1. Oh my goodness. Oh my gosh. 1 second. No, I messed it up. And shouldn't be I1 is equal to I2. Basically what happens is that you have this resistor as well, and this the voltage drop over this source here. Oh, I meshed it up. So again, so this is going to be negative Vs. This is going to be plus I4. I'm just going to assume that the resistors are the same, but you would you'd go ahead with the respective resistances to find out the currents. As you've seen here, I may have messed up. Anyways, so write KVL around each mesh, right? So you use voltages instead, equal to 0 instead of currents. You express voltage in terms of mesh currents. Using mesh and branch current relations. So if you know KVL, with your with the relations between around a loop, you basically get it, and it's gonna be the same things to solve the remaining equations, or the resulting set of n equations for the unknown n currents, and then you're done. So node voltage analysis will get you the currents, and the mesh analysis. So wrong, other way around. Nodal voltage analysis will get you voltages, and mesh analysis will get you currents. So that leads us to our final topic that we've covered so far, and that is linearity. So you might have remembered from linear algebra that for something to be linear, it needs to 1, be additive, and 2, scalable, right? Or you can multiply it by a scalar, right? This is also called homogeneity, or like homogeneous, like homogeneity. I don't know how you say it, but it's basically your scale, your vector scaling. Or scaling a vector by a scalar. All right. I will also define another thing, and that is a system. So all a system is, all it needs is it has inputs, has outputs, and it has like inner architecture. Which relates inputs to outputs. Inputs are also called excitations or causes, and outputs are also called effects or responses. I'll just use inputs and outputs for now because that's simpler and it's easier to know what they mean. Okay, so we also say if any circuit, we call something a linear circuit if every element obeys its properties. So linear circuit if and only if every element is linear in relation. So what do I mean by linear? So if I have, let's say, consider Ohm's law, right, which says voltage is equal to current times resistance. That is a linear relationship. If you think of a straight line, it'll just be a straight line. If you scale, let's say you have some voltage, you have a fixed voltage, and you scale your current by 5, you can multiply by 5, then that means your voltage should also multiply by 5 as well. If any circuit element in a circuit is nonlinear, aka it's not both additive or scalable, which means it have like an equation like this or an equation like this, like that's not a linear circuit. You might be wondering now, okay, but this is the equation for power. That's the funny thing. Power is not linear. Even within a linear circuit, whenever you use power, it's non-linear. So we can't use it for our linearity stuff. But fortunately for us, voltage, current, and resistance, it's all linear. At least for our purposes. So when we are taking a look at a linear circuit, what's special about a linear circuit is that we can scale it's this property of additivity. So let's say I have a voltage source, right? And somewhere else in the circuit, right, I have a current source, right? I'll just use some resistors just to make it more interesting and to make it look like I'm not dumb. So whenever we have a voltage, whenever you have current, if we want to add the effects of each, we can actually just eliminate one from the circuit and treat the circuit as if this current source wasn't there, or we can treat the circuit as if this voltage source wasn't there, and we can add the properties of each to each other, right? Because this current source is going to affect this resistor with some current, with this one with some current, right? If I get rid of it, that current is only going to be determined by our voltage source over here, right? On the other hand, if the voltage between, let's say, this point and this point is determined by this here, this voltage source over here. If we got rid of it, we could find its voltage just based off of this current source over here, and we can add up these individual effects to get a kind of a good picture of what's going on in the circuit, and this is something called that's not a very super way of writing it, superposition. Right? And whenever you have And if you have an independent one, you can deactivate. So you want to deactivate dependent voltage sources and current sources are not affected. So I'm just going to write that out as well. Dependent sources are not deactivated because they're considered part of the circuit and they're not considered inputs. Remember that we define the circuit as like a system, right? As a system of inputs and outputs. Our dependent sources are not inputs. They are depend on something within the circuit, right? Like consider if you had like this might be helpful for you if you're like a programmer. Let's say we have a function, right? I'm going to use C. No, I'm going to C syntax. Let's say you have a function goo, right? It takes in some inputs, right? Input 1, input 2, and you declare, let's say, a variable. I'm going to write in JavaScript. You declare a variable called g, and it's equal to, I plus I2, right? And then you return like g plus I2, right? Right. If I were to be anywhere outside this system here, we'll call this a system for analogous sake. You cannot access this g. It's dependent. Although it's dependent on, let's say, I1 or I2, you can't access it directly. Sure, if you knew that g was equal to I1 plus I2, you could technically do it. But I'm just saying, what if you didn't have access to that knowledge? Then you'd be forced to say, okay, well, it's not an input. Okay. So, some remarks here is that for DC circuits, superposition is not always the best option. You could use mesh analysis or nodal analysis, and they could probably be better. They would probably be better, somewhat be better. But a superposition isn't the only thing. For AC circuits, when you have different sources with different frequencies, superposition will actually be necessary in some cases, because there's no other way to remove the noise. If let's say you might remember from physics, like if you have like a sine wave, right? And actually, it's kind of a bad example because actually no, it isn't a bad example. I'll just use a simple case. Let's say you have two sine waves, right? And they're inverses of, so like they're reflections of each other, right? If you add them together, right, you have, well, a straight line. Right? This is destructive interference. However, you don't know, if you were to just say, okay, the voltage is 0, then you won't really know what's going on with the circuit elements due to one of these inputs. So you want to eliminate one of these inputs and find out everything using, let's say, this top one. And then you'll eliminate the top one and then find everything according to this bottom one. So sometimes superposition will be necessary when you absolutely have to. When you have something, when the inputs are different. However, that will be everything for now. Long episode. But that will be everything for linear circuits up to week 4. There will be more in a bit. So I will probably return back to this in maybe a week or 2 weeks, just in time for midterms, and I will see you there.